I thank you all for coming in such large numbers to listen, and I appreciate it. So in this presentation, we will inevitably deal with some formulas. The time has come to introduce a bit of mathematics because it is best to explain things as they are. We need to clearly understand the technique used to perform underground scans, leading to the results that Professor Malanga will present. Now the title is The Space Sonar. Sonar is a remote sensing device. Remote sensing, as a scientific discipline conducted from space, is used to measure objects at a distance. One might ask, but what does sonar do? It transmits sound waves and receives their echoes from detected objects. It is commonly used on ships and also on land or ice to analyze underground structures. But how does it work from space? It doesn't. The term space sonar is provocative because without a medium for sound wave propagation, sonar cannot function in space. Impossible? I wouldn't say that because in the end we used a space sonar. So we are here to understand how it works together. Now the agenda is tight, so I will be brief. First, I will explain the state-of-the-art of satellite remote sensing. Then, I will introduce a technique we developed to analyze how it functions and how we achieved underground scans. Finally, I will present case studies referencing the Great Pyramid of Cheops, Khufu, and other locations. For instance, we will discuss experiments conducted at the Gran Sasso in Italy, the Mosul Dam, and the Gotthard Tunnel, before handing the floor over to the professor. We have employed Synthetic Aperture Radar, SAR. I will explain what aperture means and what synthetic aperture entails, as it is crucial to understand these concepts. SAR radars are primarily mounted on satellites in space, specifically in low Earth orbit, LEO. LEO consists of circular paths in space, positioned between 400 and 700 kilometers from Earth's surface, keeping them relatively close to us. To clarify, there are two other fundamental orbits. Medium Earth orbit, MEO, is located before and after the Van Allen belts, between 14,000 and 18,000 kilometers. Satellites are not placed inside these belts due to their reduced lifespan. High Earth orbit, HEO, is 36,000 kilometers away, well beyond the Van Allen belt. What kinds of satellites are placed in these orbits? They include GPS, Global Positioning System satellites, Galileo, the European Positioning System, and GLONASS, among others. Each major geopolitical power develops its own satellite positioning system. The farthest orbit, at 36,000 kilometers, is where a satellite's revolution matches Earth's rotation. To an observer on the ground, the satellite appears stationary, although it actually moves in patterns resembling figure eights. Keeping a geostationary satellite in position is extremely challenging. The International Telecommunication Union, ITU, assigns designated slots in space where countries place satellites for telecommunications. To summarize, we have telecommunications satellites, positioning satellites, remote sensing satellites in low Earth orbit. However, low Earth orbit has become the most widely used, as recent years have seen an increase in telecommunication and internet service satellites being placed there. So, we can say that low Earth orbit is highly significant, as it provides a close connection to Earth and serves multiple essential functions. So, now let's see why it is called Synthetic Aperture Radar. So to premise, a radar, as the word itself says, is radio detection and ranging. It is a device used to detect objects that are far from it, and at the same time, it also measures their distance. And over the years, so we were talking about this, that this device was thought to be possible to build at the beginning of the century. Why was it thought? They said, well, we can use electromagnetic waves to understand if there is something in front of us. For example, it was certainly useful for navigators, and after the sinking of the Titanic, it was essential that ships had radars on board, because it is important when navigating in fog or when navigating in bad weather to have the radar on to understand what is in front of us. The problem is that it took a long time, many, many years to develop it, because in this case, let's call it the received power of the radar signal decreases with a fourth power of the distance. And this is a problem. It means that if I transmit, for example, 10, what I receive is 0.00 in terms of power. So it's a problem. So it took a long time. Some gentlemen had to invent special valves called OTVT, called magnetrons, which had the specific function of generating coherent radio frequency energy. And then this energy also had to be high power. Okay, moving forward in time, people thought of mounting or trying to mount radars on satellites. To do what? To think of generating electromagnetic images. So we were facing a fundamental concept, a concept of classical physics, precisely. A concept that in past years people had struggled with, for example, in telescopes. To visualize objects or targets that are in the distance, one had to act on a fundamental parameter. This parameter is the spatial resolution. This concept, which I will also give you a scientific definition of, spatial resolution is a distance. It is a minimum distance so that two objects can be distinguished separately. That is, if I have two objects, if I make these two objects travel in distance. So let's keep in mind this concept of distance, because later we will find it in synthetic radar. At a certain point, if we observe them with anything, with a camera, with a photo camera, with anything, at a certain point we will no longer recognize these two targets separately, because the distance is too great. And so, installing a radar at 600 kilometers altitude, one had to be careful about resolution. Physics tells us that spatial resolution, as the slide says, lambda, the spatial resolution, which is measured in meters, is equal, it is equal to lambda times r divided by 2 times the aperture. Lambda is the wavelength of the physical phenomenon that I'm using for electromagnetic remote sensing. So the entire category of light up to gamma rays, electromagnetic waves, acoustic waves. So matter also has a wavelength. De Broglie told us this back in the times of quantum mechanics. Or, for example, I can use electrons when, for example, we have to use an electron microscope. An electron microscope, electronic stands for electrons, so divided by 2. And you see that lambda and r are in the numerator. This means that the more I increase r, the larger delta becomes. But I, however, need delta to be small, because it is a minimum distance, so that two objects must be distinguished separately, divided by 2 times the aperture. Oh, everything plays out there. The aperture. If I have a photo camera to see details well, I need a photo camera with a large aperture, because I must have a wide vision of this thing, a large aperture. Try, for example, to take a photo with a camera without a lens. It can be done. But what I get is something, but it is not the photo. I obtain something, but it is not the photo. I must insert the lens because the lens allows me to see things as we are used to seeing them. That is, after a Fourier transform process. What is the Fourier transform? The Fourier transform is that mathematical operation that, professor, excuse me for the term, transforms everything that is a wave into a particle, because we are used to seeing things compressed. This pen, we see it because we have performed a Fourier transform. Our eyes, moment by moment, are calculating a Fourier transform. So, to mount a radar in space, it was necessary to design the system with a large aperture. If you do the math using the inverse formula, assuming, for example, a spatial resolution of 1 meter, you see that the required aperture in space must be huge, on the order of 20 or 30 kilometers. This means we had to install in space an antenna 20 or 30 kilometers long, an impossible thing. You can't mount a 20 kilometers long piece of metal on a spacecraft and then place it in orbit. Well, at one point in the 1950s, for example, this project was set aside due to its unfeasibility. But how can it be done? It is done as follows. There was a person named Carl Y., a scientist working for Bell in the United States, whom I would call a heretic. There is always a clash between orthodox thinking and heretical thinking. If you look back in time and analyze what happened, you'll discover that heretical thought always prevails. Heretical here implies aero, air, or freedom. Essentially, Carl said that it made no sense to install a 20-30 kilometer antenna in space. It was stupid and useless. He proposed, cut a piece of this antenna, say 6 meters long, cut it with a flexible tool, take the rotor, and actually cut it. Then take this fragment of metal, package it, load it onto the spacecraft, and launch it into space. The orbit will then synthesize what we need, even an 80 kilometers antenna. We later used this approach, and I take the opportunity to thank the two American providers who supplied, free of charge, not only to us but to the entire scientific community, all the satellite data with an 80-kilometer aperture. An 80-kilometer aperture provides a ground spatial resolution of about 6 or 7 centimeters, which is very good. Now, imagine a satellite flying in space. Remote sensing satellites usually travel in a circular orbit, alternating between the south and north poles, while the Earth rotates underneath and the ecliptic remains constant due to geodetic physics. Thus, the Earth rotates under the satellites at least once a day, allowing them to capture an image of any point on Earth daily. This makes them very attractive from a scientific standpoint. Having solved the aperture problem, we perform scans divided by time. Virtually a long aperture, as long as we want, even 80 to 100 kilometers, doesn't matter, because what matters is achieving the highest resolution on the ground. So what does the satellite do? I won't go into excessive detail, but I'll explain it simply. When the satellite performs a scan in the direction of its orbit, called the azimuth, it transmits electromagnetic pulses toward the Earth and receives their echoes. These echoes are digitized and stored in onboard memory, and when the satellite reaches a downlink point, it sends the data to Earth. The data are then distributed to users. Usually they are not directly usable but must be processed to obtain an image. For example, look at this little device you see here. As the satellite follows its orbit, you can observe that the waves it transmits are compressed on one side and expanded on the other. This effect is called the Doppler effect, which explains how the azimuthal component of the image is synthesized into sound, because by chance, the Doppler band falls exactly within the acoustic band. So, with Professor Malanga, we have focused our efforts a bit on this word, acoustic, because we were interested in looking under the pyramids. We must all understand that the electromagnetic interaction with matter is only superficial. One cannot do miracles. Yes, I can be able to transmit 1 gigawatts of photonic energy and maybe get 20 or 30 meters of penetration, but forced into the matter. Yes, but who gives you those 30 or 10 gigawatts? It's impossible. So, we thought of exploiting acoustic energy, exploiting the phonon, because sound is the physical manifestation of sound, which is nothing other than the vibration of matter. It propagates very well in matter, and the denser this matter is, the higher the speed of sound propagation. Therefore, granite is perfect for sound, and this is important. This is a synthetic aperture radar, so it transmits signals, the so-called SAR signals, made in this way to resolve the range dimension, while in the azimuth you see the Doppler effect. It has happened to all of you that, while driving the car, you encounter another car coming towards you that sounds the horn. When the car is approaching, the horn produces a higher frequency compared to the frequency at 0 Doppler, which is the frequency for which the horn was designed. Then, as soon as it passes us by, we hear its original sound frequency, and when it goes behind, the frequency drops. This physical phenomenon is used to solve the other dimension of the image. For me, it was important to try to explain this with simple words. You see here the diagram. We have a satellite radar. This is the drawing of TerraSAR-X, a very good German radar. You see it flies along the orbit, and let's suppose it has to take a photograph of these 3 houses. What we receive, you see, are these echoes. These are the radar echoes, you see. These are the data we receive, and they are only these. It's not that we immediately see the images of the houses. They must be processed, because this image you see is like the one I mentioned earlier, taken without the lens. Because here, we still need to perform the Fourier transform. And how do we do the Fourier transform? We do it like this. We take the transmitted reference signal, the so-called SAR signal, and we perform the convolution integral with the so-called distance part of these droplets that are here, and we are performing what is called range compression. Therefore, we are trying to resolve the first part of the image. You see, then we have compressed the first part of the image. Then by taking the reference signal, meaning the Doppler frequencies we received, we obtain the 3 objects. So we went from a wave situation, and after the Fourier transform process, we have the particle, and the particles are well-defined, localized in space-time, because their localization is always done at 0 Doppler. This is an important parameter. Okay, you see, this is another example of focusing. You see the objects being visualized not as dots, even though they are particles, but they are visualized with a particular function, namely the cardinal sign, which is the sine of x over x, the so-called sync function. This helps understand another very important concept that Professor Malanga has stressed, I don't know for how many years, in explaining precisely the difference between territory and the map of the territory. So we human beings who are here, it will always be impossible to visualize the territory. But what we look at, even with equipment, in this case with radar, is always a map of the territory. This means that our map of the territory is this sine x over x function, and this is since. We will never see a dot, but we will always see a function that approximates the dot. Okay, here we can go ahead. This is the focusing part, both in range and azimuth, to get the satellite image. And then finally, ladies and gentlemen, we arrive at the function, our two-dimensional sine of x over x function, where we have the resolution values in the range and the resolution values in the azimuth. We have finally obtained a satellite image, and I will show you some applications of synthetic aperture radar. For example, it is necessary to mention what is found today in the state of the art. What is the use of synthetic aperture radar? We use it massively, for example, for monitoring or control of the territory. It is very important because synthetic aperture radar has very high precision, sub-millimeter precision. This means that if I position the radar in space and look at an object on the ground, if this object moves slightly, the radar will detect it. The radar is capable of detecting sub-millimeter movements of objects on the ground. I will show you this very simple, brief video.
Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see two bright spots on the bottom of the box.
Stiamo simulando un interferometro.
Then the wave from one slit can interact with the waves from the other slit. I've got a demonstration
Abbiamo
here
due
of a little pond
sorgenti
where we can see this with water waves.
elettromagnetiche coerenti,
Two
vedete?
sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular
Stiamo
waves.
generando energia elettromagnetica coerente con un primo radar,
Second source of ripples,
con il secondo
then we
radar,
start getting an
vedete?
interesting pattern.
Cosa ottengo? Ottengo una figura di
This
interferenza.
pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference.
Constructive interference, that is, we obtain in space areas where the density of electromagnetic power is null, destructive interference, and areas where the power density is very high, constructive interference. Okay, what is this useful for? This helps us estimate. You see, when I use two radars, for example, I can estimate the so-called interferometric fringes of the Earth. These interferometric fringes help me estimate the Earth's topography. In the 1980s, thanks to the SRTM mission of the shuttle, a topographic survey was conducted, allowing for the first time the mapping of the entire Earth's topography using synthetic aperture radars, a so-called interferometer mounted on the shuttle. What is this useful for? For example, this technique could help us. Okay, the video is not playing, but it doesn't matter. I'll describe it verbally. Estimate the fractures of the Earth. These fractures are estimated to study earthquakes and the movements of the Earth. Okay, so here we move more precisely to what we have done in this project. For this project, I will briefly describe how to transform photon energy into phonon energy. This is important. Together with the professor, we noticed that any photograph, whether taken with conventional cameras or with synthetic aperture radar, has imaging imperfections. It is always blurry. Why? Because everything moves. Maybe you can't see it well with a regular camera, but as I mentioned before, radar has an extremely high precision and is capable of detecting sub-millimetric movements of the Earth. Okay, and so what did we do? We invented a method called the Doppler sub-aperture method. Instead of using the entire orbital synthesis to generate an ultra-high resolution image, which was unnecessary, We tried to see what would happen if we sacrificed some ground resolution. For example, we reduced the resolution by half. We accepted looking at things with less detail. No problem. And so, we synthesized images using half the Doppler bandwidth with half the orbit, and then performed a temporal scan of the orbit. This helped us demonstrate that it is possible to transform an electromagnetic wave into an acoustic signal. Why? As we conducted the intraorbital scan and applied pixel tracking algorithms, we noticed that these pixels moved coherently with the movement of the Earth. Everything moves. We applied this movement estimation to the pyramids. We already knew that the pyramids were subjected to vibrations, by the wind, first cause, by human activities in Cairo, second cause, and by an extremely important phenomenon, the photon-phonon interaction with matter, in the sense that synthetic aperture radar transmits electromagnetic pulses to the ground. Some of these pulses return to the receiver. Another part is transformed into phonons. These phonons were very precious because we realized that they maintained the coherence of the transmitted signal. These phonons traveled underground. They were, so to speak, reflected, meaning they bounced back from the materials they encountered underground and could be detected again as evanescent waves on the Earth's surface. This was something we had never considered. We were speechless. It was feasible. By detecting these Doppler anomalies, interpreted as evanescent waves visible on the Earth's surface, what did we do? We designed a space turntable, where the disk, the vinyl, equals the Earth. The turntable needle equals the electromagnetic wave, the light, the photon-phonon interaction, the stylus, the interface that transmits and modifies the information, transforming it from one nature to another. Okay. Then practically our appetite grew as we worked. We didn't immediately start looking underground. First, we wanted to understand what was happening. What magnitude were we dealing with? How strong were these vibrations? Let me show you an example. We estimated the vibrations of high voltage power lines. I don't know if you've ever noticed, but when you pass under high voltage power lines, you can hear a ripple. That sound is caused by high voltage, making the cables vibrate. What we hear is the noise. We captured that noise from radar, from space. Then after conducting these experiments, we said, Corrado, we need to develop an algorithm to perform the so-called tomographic inversion. What does tomos mean? It means slice. If we had the ability to estimate evanescent vibrations on the Earth's surface, then why not look underground? Because mathematics tells us it is possible. Here you see a model we developed using springs. These springs were attached to masses. By performing the Fourier transform of the acoustic signal, we recreated the lens that allowed us to see underground. Okay, now I'll show you some past examples of our work with Corrado, mainly to emphasize an important validation we received. I want to thank a very kind gentleman whom I respect deeply. He did us a great favor. Even without knowing us, he validated our technique in the Scan Pyramid project, months after we had already published our discovery of the famous corridor, now called the Corridor of Discord. He confirmed our theory, so I am very happy. In fact, I thank him for validating our technique. Okay, I apologize if I am a bit tedious with formulas and explanations, but unfortunately, we all need to understand this together so that we can be more confident in our findings. Now let me show you a couple of cases where we applied the radar to acoustic conversion technique. One example is the Gran Sasso Laboratory. The Gran Sasso Laboratory is a physics research facility located about 1,400 meters underground, measured from the summit of the Gran Sasso. Here is a tomographic image we estimated, one of the first we made. I always like to show it because it's beautiful, and honestly, it's almost like a bazinga moment. We managed to see the INFN, National Institute for Nuclear Physics, along with parts of the tunnel system. Another case study, the Mosul Dam. This enormous dam has an internal service tunnel. We produced a tomographic image showing the gallery inside the Mosul Dam. We even detected the turbines. Lastly, a case study of the Gotthard Tunnel. We created a tomographic image of the underground structure, and you can clearly see the tunnel inside the mountain. Final note, this method has been submitted as a PCT international patent. Currently, the patent is active in Malta. We'll see what the future holds. I'm done. I'll now pass the word to the professor.